Okay, guys, Math 6500, MLE for regression, and some more stuff. Don't you love the vagueness? This is this is a very important video, and I don't want to minimize the effect of any of the others at all. All the videos go together to create a foundation for what we're going to do in 6500, and because we're reviewing 5500 material now. But I got to be honest with you and tell you that there are certain videos that play a more important role. Of the two videos that, again, they all go together to create the framework, the foundation, if you will, for 6500. But there are a couple of videos that are just more important, more crucial, more beneficial, I guess, for where we're headed. And I tell you that because if there were two videos that I would encourage you maybe to watch twice, it would be this one and the one for the assumptions, which I think is the video that I put up prior to this one. So, I know in all of your free time, and we've got nothing to do but sit around and watch Darbro videos, right? Not that you guys have jobs and families and responsibilities and all that stuff. But, all kidding aside, this video and the previous video, I would, hope that you do take a chance to watch it twice. All right, guys, concepts from MLE, the maximum likelihood estimation, carry over to estimating parameters. So MLEs carry over to the estimation of the parameters. For the normal error regression model. The normal error regression model is simply this. Now, guys, let's go through and just so there's no misunderstanding. I want to be very, very thorough in this video because simply of its importance. The Y sub I is the observed response for the ith trial. The X sub I is the level of the predictor. And we talked about this earlier because at each level we assume that we have normal distribution with equal variance where the mean response is the center of the distribution. So the X sub I define that as just the level of the predictor on the ith trial. The beta 0 and the beta 1 are the things that we're most interested in here because those are the parameters of the model. And then the errors are something that we assume to be, I'm going to put one of the classic Darbro thought boxes here. We assume these things to be independent. And we assume those to be normally distributed with mean 0 and of course variance sigma squared. All that tells us this part is that at each particular level let's just choose an arbitrary level here, and we've got our model here. At each particular level of X sub I, we have a mean response, and then the values of Y sub I at that particular level are normally distributed with particular variance. Now, if I take this and rotate it, I'm still going to get the normal model. So in the center I have the mean response for Y at that particular level, and then we have standard deviation sigma that's consistent at each of this levels. So that's really all I'm talking about there. So let's just dive in head first and, look at an example. And let's say given the following data. Let's go 25 and 5512 and 3010. Let's hope this works out okay. I haven't calculate the likelihood important word there, okay. Calculate the likelihood value for the parameters beta 0 equals 0, beta 1 equal 0.5, and the variance is equal to 9. So guys, clearly our standard deviation is equal to 3. Now, the first thing that I would want you to do here is to think about the the ith response. So we have 3 levels that we're investigating. Need some music in the background, people. And what we're interested most of all in first is to find the mean response. And I forgot what our betas are. So really this is just a matter of putting, I'm going to put the 0 there, just putting the x in this model. So guys, clearly the mean response here would be 10. The mean response for this would be 27.5, and the mean response here would be 15. Now let's investigate this just a little further. So what we're saying here is at when our level is 20, and we've got our regression. I should have gone through the origin because we have beta 0, 0. We have normal distribution where the mean response is equal to 10, and the standard deviation is equal to 3. So we can get into this a little bit more. And we can say the distribution of the y sub i's at this particular level will have mean 10, standard deviation 3, so one standard deviation above the mean will be 13, and one standard deviation below the mean will be 7. So we know that about 68% of our y sub i's, using the 68, 95, 99.7% rule, which you guys are probably teaching to your students in high school, will fall between there and there. Now, what we're looking at is we're, in this situation, focusing on the y sub I, which is equal to 5. So that's going to be about right here someplace. Now, here in a minute, we're going to talk about the density. So the density of 5 is just going to be the height, is just going to be the height of the, well, I can't get it to work here, guys. It keeps wanting to do wacky stuff on me. You guys aren't seeing this good thing. So it just turns out to be the height of that line right there, the density. And, we're going to talk about that a little bit more. I'm going to talk about it actually a lot more. Okay. Now, 2 ways to calculate the density. And one of them I think is easy, and one of them, well, actually both of them are easy, but one of them's a lot easier than the other. One way is just to use R, and there's a function called dnorm, and the first thing we put in is the value at which we want to calculate the density, and then we put in the mean and the standard deviation of the distribution. Obviously, norm implies that we have a normal distribution. The second way is we know that we can find the density in a normal distribution simply by looking at the model. One of the toughest things teaching like this is predicting the space that you're going to need. All right. So we could use this. Okay. Now this is the easiest, but considering where we're headed, I want you to be able to use this as well. So guys, the density for the first observation, which is 25, can be calculated by taking my y value at that level was 5. And essentially the beta 0 minus beta 1 is just going to be the mean response, which is 10. Let's think about it, guys. This part right here, and I'm going to erase this, is beta 1 x sub I. So what's going to go right here is 0. What will go right here is 0.5. And then the x value, guys, please forgive me for this, is going to be 20. So essentially what's going to go right here is just 10. So I'm going to use the power of the eraser. And I need to allow some space here, don't I? And of course this part right here is going to be the standard deviation, which is 3 squared. Now let's just go ahead and take care of this. This is going to be 1 over well, this is 3 square root of 2 pi, and this is going to be e to the negative 0.5. It's going to make it a little bit easier. And let me grab my calculator. So we've got, I'll tell you what I'm going to do. I'm going to just simplify the exponent here. So we've got negative 5 divided by 3 squared times negative 0.5, and I get negative 1.389 here. So guys, let's go ahead and clean this up a little bit. So again, I'm just going to use the calculator on this. Silence is deafening, right? And I get 0.0332 for this. Now, a much easier approach to this calculation is going to be to use R, and I want to illustrate both to you. So let me get out of here and get this started. So guys, if I bring R up, what I can do, and I can do the density for the first observation using d norm. And of course I want it at the y value of 5 with a mean of 10 and a standard deviation of 3. So guys, d1 is exactly the same thing that I get using the formula. Now, let's go back to this. Now, the next thing that we know is we know that the likelihood function for n observations is the product of the densities. So we know that the likelihood function and this has, again, we have the IID property, independent and identically distributed. We know that the likelihood function for n observations and let's just is the product, not really sure what I want to say here, of the individual densities. All right. So guys, at the end of the day, we can say that the likelihood given these parameters will be the product of I'm going to use a little different notation here. I think it's going to make it easier. Well, I know it's going to make it easier. And let's see, we're going to get 1 over, actually that'll be a negative on it. About to run out of space. Okay, let me go to the next page, and this is going to be easily, let me see what's going on here. So we've got the products, so we're going to have, we'll have n of these. And then we're going to multiply these terms. We're going to have, we'll be summing up the exponents. So the minus 1 over 2 sigma squared will be in each one, so we could factor it out. But then we'd have to sum up those, I think. Yes, yeah, okay, good with that. Now, so guys, the values of beta 0, beta 1, and sigma square that maximize this likelihood function. Whoa. The likelihood function are the MLEs. Which would be denoted for beta 0, it'd be beta hat 0. Guys, sometimes we use B0. And beta hat 1. And sometimes we use beta 1. So these are just the estimates of the parameters. And also, I'm not going to make too much out of this here because we also have that. And you know, just while I'm on it, the solution to this, which is going to play a role when we get into the ANOVA, is this. So, guys, obviously, these are the same estimators. We get when we do least squares. Be kind of a wacky procedure, wouldn't it, if we did least squares and did MLEs and we got different answers? So, guys, again, by the time you all the smoke clears, we can see that for these three numbers, the beta 0 is 2.81, and the slope is 0.18. Now, I got to admit to you, I cheated and did these on R, but that's what we get. Now, this whole MLE process, let's review this. It's been a while. So let's review the MLE technique, and then we'll implement it for regression. So let's take a mass function. I don't know which one. All right, I'll tell you what. Everybody's favorite, right? Let's take a look at the MLE technique for the Bernoulli mass function. And we know that f, given our data, and the parameter here would be theta, the Bernoulli function looks like this. And what I'd like to show, that the MLE is nothing more than the mean. So, given some data, we can, and these data are independent and identically distributed. All right, guys, I'm losing my train of thought here. We can show that the MLE is the product of the densities. So is going to be now, typically I don't use the multiplication symbol, but I want to do it in this situation. Got to run out of space. Yeah, so we get that. Now, guys, I want to simplify this. And looking at the first terms, we can see that this is just going to be theta x1 plus x2 plus xn times 1 minus theta, which would be 1 minus x1 plus 1 minus x2 dot 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 1 minus xn. Now it should be pretty clear, therefore. Then we can set up the likelihood function by taking the sum of the x's. So we've got 1 plus 1 plus 1 n times, and then minus the sum of the x sub i's. So the first thing we'd want to do is set up the likelihood function, which we just did. Now our next step is take the natural log of the likelihood function. So the natural log of the likelihood function, which we just created, will be the natural log of sigma sum xi 1 minus sigma n minus sum xi. As we can clearly simplify this. Using this approach. Yeah, we could clean that up, but I think that'll be fine. Yeah, let's just leave it like that. Now, guys, our next step is to take the derivative. So I'm going to take the derivative of the natural log of L with respect to the parameter, which in this case is sigma. So the first term, we're going to have use the product rule. So the derivative of first times second, second. So the only thing that's going to apply here will be and then the same thing for the next. So derivative of the first times second, 1 over. Then we got the chain rule that we got to apply, so we have to remember that. So we're going to end up with, let's see, n minus sum xi over 1 minus theta. So we got to multiply by -1 because of the chain rule. So gang, this is going to be equal to the sum xi theta minus n minus sum xi 1 minus theta. Now the next thing we have to do is set this equal to 0. And I mean, you can see setting this equal to 0 that we're ultimately just going to have two sides set equal to each other. Well, I would cross multiply. And you see something kind of cool here. So guys, this would clearly lead to the MLE. Remember, the MLE is an estimate of the parameter, so we put that over it. Yeah. Which is X bar. All right, guys. That leads us to repeat repeat this process with our regression model. So first of all, we know that the density, as we talked about earlier, at a particular level is this. So our likelihood function is going to be the product of the densities. So in other words, d1 times d2 times dn given x1, y1, 2y2, xn, yn. All right, gang, so the likelihood function given our data for the parameters will be equal to the product and I've already given you this. I'll tell you what, I've already given this to you. I'm just going to go ahead and simplify, give you the simplified form. So that would be 1 over 2 pi sigma squared to the n over 2 e to the minus 1 over 2 sigma squared times the sum of y. All right. Now our next step, just as we did before, let's take the natural log of our likelihood function. And the natural log of the likelihood function is going to end up being minus n over 2, natural log of 2 pi minus n over 2, natural log of sigma squared, minus, I remember the first two, so 1 over sigma, okay, minus 1 over sigma squared times the sum yes. All right, gang. In the Bernoulli example, we had one parameter, theta, but in this situation, we have 3. You know, just kind of assuming that this value is given, so that makes it a constant. We have 2 parameters, so we need to look at the partials. So I need to look at the partial of the natural log of the likelihood function with respect to beta 0. And guys, this is going to turn out to be 1 over sigma, or sigma squared. And the partial with respect to L of A, I'm sorry, with respect to beta 1 is 1 over sigma squared gives us this. Now, when we set these equal to 0 and set equal to 0 and simplifying, what we actually end up with it's really easy to remember if you see the bigger picture. As we end up getting this system of equations. Now, let's go way back when, and let's reconsider the least squares approach. If I'm going to think about all the videos that I've put up so far, the most important video I think is the one I'm doing right now. The second most important video would be on the assumptions. And the third most important video would be on the least squares. So if you remember the least squares, we create this Q. And the goal is to find the minimum value of Q, which is just the sum of the least squares. Now, this approach led to the normal equations given this. Now, if you think about it, this can be rewritten in matrix form. Now I'm going to switch and put the right side first, but you guys are clever. You'll figure it out. And you may have to verify this, but this is nothing too crazy. Leads to this, which clearly, guys, can lead to us finding our values for beta 0 and beta 1 by multiplying these two matrices. Now, if we return to this form, and if we solve this simultaneously, well, we get some cool results. And don't get too tore up about this. Really, all we're saying is to find our estimates of beta 0, beta 1. There are numerous approaches. Least squares. I'm going to need to go to another page here. All right. So guys, pretty thorough illustration there, trying to connect it all together. At the end of the day, if I'm going to come up with the coefficient or the estimates of beta 0, beta 1, I'm going to use matrix approach, which is going to be something we're going to get into very, very soon. But right now, if you have data, whatever it may be, whatever it may be, and you want to find beta 0 and beta 1, what are your options? Well, technology is by far the easiest. That's what I teach my 1500 level students. The TI-84, use R, SPSS, whatever it may be. But getting into, really learning what's going on here. One is least squares. Another is maximum likelihood estimation. And another would be the matrix approach. So gang, that's all I got. I think this was kind of a long video, but it's an important one. If things didn't make sense, you might want to consider watching this one again. So that's up to you. All right, take care.